So now let's try to do, so everybody says that coverage function is submodular, right? Why? Because you are saying that, okay, so let's just take two sets X, subset of 1 to m, or okay, or rather let's say, let's apply this definition, right? So we took some A subset of B, which is subset of 1 to n, right? And what is f of B is basically union of uh, I in B fi, right? And what is f of A, I in A, J in A, Fj, right? Now you picked up an element which is in E, which is in B minus, sorry, 1 to m minus B. Let's pick up that element U, or let's say L in this. Now what are you looking for? You are looking to add, okay, how many new elements does this add, right? So what is the meaning of F L A, right? What is the meaning of F L A, right? So it basically tells us number of new elements that is covered when FL is added to right. This is what it means, right? And what is FL of B tells us same thing when FL is added to I in B F I. But let's look at the elements which are covered with respect to A. Is this? These are the new set of elements which are covered. What are the elements that are covered by B? It is definitely this and maybe some more, right? Because every set, because A was contained inside B. Now you take any new sets and look at the new set of elements that are covered, which is not in A, right? So those guys are going to be, right? So look at, is going to be here, right? So clearly with respect to him, you might be covering more new elements compared to the blue guys, at least as much as you will cover with respect to A, right? And this is why this is submodular. Good. Okay, and there are several such examples. So there are two fundamental questions which are studied with respect to submodular functions. So two important questions. One is called submodular minimization, and another is submodular maximization. Okay. So given f, what is our objective? Okay, f from 2 to the power, say, universe 2 to the power m to r, right? And this is any function, okay? But how does this given to you is also an important question. Imagine that this is given to you as an oracle or somehow in some succinct encoding. Okay, is the rank function of a matroid submodular? Think about it. So what is a rank function? Okay. So this is a classical thing. So let me write it down. So you have universe and you have a family. So this is my matroid M. And what is my rank function defined? Rank is defined from 2 to the power u to the natural number. So what is rank of any set X? It's basically Y subset of X, let's not call it F, independent set, Y subset of X, Y in Li, first of all that, and okay, cardinality of Y, max of cardinality of Y, Y subset of X, Y in I. So basically it's a cardinality of those sets which are independent and contained inside X, take the one with the maximum. Show that this is some model. Okay. And what is my goal? My goal is to output A subset of n such that, or goal is to output A in arg min A x in x subset of n f of x. Okay. So look at all the sets which minimizes the function f of x, just output minimum. Okay. Sometimes just value. Okay. There is another one, some modular minimization is like, it's called constrained minimization, like k constrained minimization. K constrained minimization. Like what is this? Not only I want x subset of n, I want mod x should be less than or equal to k, and I want to find min. Okay. Does this question make sense for submodular minimization? No, because generally we assume that f of phi is 0. So for many problems this doesn't make sense. Okay. So anyway, just leave it. Okay. Because then you are looking to minimize anyway, so I'll give you an empty set, right? So for minimization, but until unless you could have R being negative also, right? So we can have this, but then you demand that mod x is less than or equal to k. But what is submodular maximization? Same, right? Same, but goal is to find or output A in arg max x subset of n f of x. Okay. And what is the k constrained version of this? Mod x. Additionally, I want x to be mod less than or equal to k. But here, this problem is polytime solvable. Okay, this is p time solvable, polytime solvable. This is NP hard. Can you say why this is NP hard? At least this version. Huh? Max cut. Yeah. Right. So max cut will give you that this is NP hard. Max k coverage will give you that this is NP hard. Right. So this is NP hard. So maximization is NP hard in general. But if we had a good approximation for this version, then I can get a good approximation for this version. Right? If I have a good approximation for this version, then I have a good approximation for this version. Agreed? Okay, excellent. Right? But personally, I actually don't know this algorithm. Right? This is one of those my wish list that I should know. So I will not even touch that. Okay. So what we are going to go to this. So we will concentrate from now onwards on submodular maximization. Okay. Okay. And that's also on this version for now, because once we have a good approximation for this, I can give you a good approximation for this. Right? So let's concentrate on harder problem, because this implies a good approximation for here will imply a good approximation for here. Okay. There's some special case. So can you tell me a good example of submodular minimization? Min ST cut. Okay. And as I told you, right, people just assume that you have a value oracle for this. Okay. The model in which you have a value oracle for x. So if I tell you set x, you will have to give me f of x, right? So in that model we want. So like lots of graph problem, this it is not a very big thing because I can compute it myself. And this is what I meant by succinctly given, or you give me an oracle when I ask this. Okay. So if we, not in this course, but if I feel like I'll teach you this. Okay. So there is another special kind of submodular function. Let's concentrate on that. Okay. Another special family of submodular function. These are called monotone function. So what is monotone function? Like for all a subset of b subset of n, f of a is less than or equal to f of b, right? So this is what is called monotone. Okay. Okay. So first let's concentrate on, we'll concentrate on monotone function because it is slightly easier to handle, and then we will say, then we will see why it is not easy to handle non-monotone function or general, and try to come up with some strategy to work around it. Okay. Okay. So let's get started. So goal. Goal. Let's say okay. Let's assume that f is non-negative submodular. Okay, f is non-negative submodular non-negative submodular. Okay, right. Non-negative monotone submodular function. Okay. Do I need this? Let me see. No, I don't think I need this. All it is monotone. Okay. So let f is monotone submodular function. Okay, this is given to me. Output a set of size at most k. Okay, at most k. that maximizes, okay, set of f that maximizes f value. Okay, so that's my goal. So what should be a reasonably greedy algorithm? So let's make, right. So this is where I'll try to use the utility margin thing. Okay. So suppose I change this. Now it takes. What should I do? Repeat or whatever you want to say. While mod s is less than or equal to k, what I want to do, add. So in the beginning, I have put s equal to empty set. I have not picked up anything. Add to s an element I, okay, that maximizes the utility, okay, that maximizes the marginal utility or marginal contribution. So that should be that maximizes, that's it. Okay, f is monotone submodular function, and I also assume f of phi is same. Does it already, that automatically imply this is non-negative, right? No, because phi is contained inside everybody. So this is fine. Okay. So what do you think? How should we go? So suppose this is an algorithm. So if you have not seen, if you have not played around with some modular function, it is slightly harder to see. But we have seen the, what is that called? But we have seen proof of this already. It's just that we have to learn to play around with submodularity. Okay. So let Si be the solution after ith iteration. Okay. I is between 1 to 2. Okay. Of the greedy algorithm. And let A star be the optimal solution. So when we were trying to do greedy for, forget about it, for maximum coverage, this is also like a maximum coverage. This is one example. I want to optimize the max value for the k sets, right? So I just want to lift the approximation algorithm for maximum coverage to a much more general setting of monotone, submodular, non-negative, like monotone, non-negative submodular functions. Okay. So what was the first thing? If you recall, we set up some Zi. So basically we said that each time a new element is added, it adds, like, I mean, at least you have covered opt by k factor, which is the same thing as saying that whenever I add a new element, its marginal utility or marginal contribution is at least opt over k. If I can show its marginal contribution is at least opt over k, then maybe we have a, because then in the induction hypothesis we were just doing not much, right? Then we might get 1 minus 1 by E approximation algorithm, which will be much more general than max coverage, because max coverage is both non-negative and it is monotone, right? Okay. So the hard part is to coming up with this, that every time I add a new element, somehow it eats away from the total cover some 1 by kth fraction of opt, okay, and that's a bit hard. Okay. So now what can I say? I can say f of s star is less than equal to f of si union s star. Why I can say this? This is monotonicity. Otherwise I cannot say this, right? Otherwise I cannot say this, that this is done deal. Okay, good. And let's assume that S star is equal to x1, x2, dot 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 xk. Some k element. This is your optimum sets. It doesn't matter, I can choose any k elements, because even if there are small subset, I just add randomly some elements, because that will not increase the value. Look, now it is not necessary that the k sets will always be the right answer. Maybe the right answer is subset, but since it's monotone, I can just add some more elements and make it exactly equal to k, and I would lose nothing. Okay, so this is why I can assume that S star is x1 to x3. So you have to keep these things in mind, because when you have streaming algorithm, these things will go. Okay, so like it's just playing around with this. So what is f of s1 union s star? So I'm just going to write it down like the way we were doing the proof, right? Oh, this implies this, that implies this. I mean, okay. But you understand what my goal is. It's exactly like coverage. I would like to show that utility, whenever you added the ith element, we have taken away whatever f star by k. If like at least you have achieved f star divided by k, and then we will try to set up other things. Okay. Okay. So this is equal to, I mean, I can actually write equality. Okay, let's see. Please tell me if I'm writing something wrong. So I added f of si, f of si union xi minus f of si, right? So nothing, I just added and subtracted, right? I'll write more things, okay? Look, then I will add 2 elements, subtract 1 element, so that I have this, okay? So f of s1 union, so this is not xi, it's a x1, okay, x1 x2 minus f of si union x1, okay, plus f of si union x1 x2 x3 minus f of s1 union x1 x2 dot 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 dot. What will be my last term? F of si union x1 x2 agreed? Now notice this term is going to survive, rest are like they are going to cancel each out, right? Except what? This term and this term. This term is not going to cancel out each other, and that's okay for me, right? Because this I added, because this is what the term was which is surviving here, and then I have 2 terms which cancel out each other, right? Okay. So this is less than equal to, right. So this is all equality. Is this okay? So this term I just wrote it down, okay. But what is this term? This term is, with respect to this, it is utility of adding x2. With respect to this term, it is utility of adding x3, and so on and so forth. Agreed? So this is nothing but f, just one second. Okay. So ideally I should write here, if this is what it is. What is this? It is of adding f of x2 to what? Si union, right, plus f of x3 to Si union okay. Is this fine? Or I'm writing something bogus? Is fine, right? Okay. But notice, now I would like to use sum modularity. What does sum modularity tells us? It tells me that, look boss, this term is less than equal to if I just added x2 to Si, because Si is contained inside Si union Xi. So this is plus f x2 Si, f x3 Si, dot 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 f xk f xk So look at these terms. What is the property of f of x2 Si? Now if I Wait. Look at this term, right? Look at this term. Either x2 was already there inside, right? Or it was not there. If it is there, then adding to him will contribute to what? Nothing. Okay. So let's weight this term here. I'll come back to that term. Okay. Okay. So what does this implies? Look at f of x2 added to Si. What is the meaning? So why couldn't I write this as just adding x1 to this, right? So let me write it down this as nothing but okay. Now notice that fxi fi or fxj si is equal to what? By definition, it is f si union xj minus f of x minus f of si, right? Now what element did I add at that point? Which maxima is this? So there are two cases. If you look, so clearly whatever I got in Si plus 1, right, that guy's marginal utility was larger than anybody's marginal utility, right? So it means any of these term is less than equal to f of Si plus 1 minus f of Si. Because what am I doing? Look, I have some S, right? Add to S an element I that maximizes this, right? So this quantity is, this is what I am trying to compute, right? And this is the maximum for all of these guys. Okay. So if an element is not present, this is perfectly fine. And if an element is already present, then it is 0. So this is perfectly less than equal to this. Look, it's possible that the element which I am considering, Si already contains this, right? But then what is the utility of that? So Fi S union this is 0. So this is less than equal to any set I write. So this is less than equal to k times f of Si plus 1 minus f of Si. Agreed? Right? But what was f of S star is opt. So what do we have now? Opt is less than equal to f of Si plus k times f of Si plus 1 minus k times f of Si, right? Is that correct? Okay, so that implies opt minus f of Si divided by k is less than equal to f of Si plus 1 minus f of Si. Is this correct? I just did the manipulation. Right? Okay. So now, so when I added, I have more or less showed to you that you are adding some 1 by k fraction of the optimum. So now what do you like to show? I want to claim, okay, see, so like when I was doing some normal coverages like opt covered, all this, I'm still doing the same. It's just that I have to write it in a proper way so that it comes out, right? And here I have used the monotonicity very nicely. Otherwise, I would not have been able to say these things, and you will see a counter example in a minute why this will not even work. Okay. So now I'm going to use induction to prove the following. What is my induction? F of Si is at least 1 minus 1 by k times opt. I want to show this. Is this true for I equal to 0? What is I equal to 0? F of S0 should be at least I equal to 0 is how much? 1. So 1 minus 1 is 0 and opt. So this is fine. Right? This is 0, which is fine. Because what is f of S0? Is f of empty set. Because S equal to empty set. Now what is f of Si plus 1? Right? Is this quantity? Right? F of Si plus 1 is this plus f of Si1. This is why we got this inequality, right? So what is this f of Si plus 1? Is at least f of Si plus opt minus f of Si by k, right? Which is equal to f of Si plus opt by k So if I take this common, what do I get? Okay. Now let's apply induction hypothesis on f of Si, which is at least this much. So what do we get? Agree? Which is equal to 1 minus 1 by, like, which is equal to this into opt. So this is into 1, which is opt minus opt by k minus 1 minus 1 by k times I plus 1 times opt plus opt by k. This will get cancelled, and if you take common, then 1 minus 1 by k to the power I plus 1. Right? So f of s, which is equal to f of sk, is at least how much? Right? Which is equal to 1 minus 1 over e times opt. Okay. So this greedy algorithm is great. Right? So if you are looking for submodular maximization, and if you just know how to do it for k, you do this, and then what will you do? Right? I just do it for, I run from 1 to n if I knew the universe size, right? So I apply this k for 1, 2, 3, n, and whichever returns me the best, I return you that. Clearly that's for unconstrained version. So this is how you can get 1 minus 1 by e approximation for unconstrained version if your function is monotone and non-negative. Okay. But what happens if function is arbitrary? So it's submodular, but it is arbitrary. Is this greedy algorithm going to work? And we are going very slowly, but like we have to build it towards it. Otherwise, okay. So there are two questions we should carry. So first, let's see that why this is not going to work for non-submodular, like for arbitrary submodular function. And second, what should we do to make it work in streaming setting? Right. So there are two questions to address. A, is this greedy algorithm works also for arbitrary function? And B, how do we make this into an algorithm in streaming setting? Right. So when we were doing just coverage, it was easy, right? Things came, we saw how many covered, and we were able to do a lot of things. But here, what will you do? I'll tell you what is the difficulty first in doing this. The problem is why can't I do again that? So what were we trying to do? Let's try to add an element, right, which does 1 by k of something. Like, I mean, all I require is that it satisfies somehow this inequality. Yeah, I mean, if I can look, this is an easy quantity to find, no? If I know f of Si and I have to add one extra next element and I have to check something and I know opt, suppose I knew the value of opt like z, somehow I will be able to guess that up. That's not very easy, that's not very hard. We can do it in parallel, guess the value and like do a lot of things, but okay. Suppose you knew the opt value, okay, what will you do? The problem is that the element which has gone by, because it was not adding too much, maybe after some sets has been added, it has started to add value to it. So the element, it's not guaranteed that, like, so the thing which we use in coverage is that among all the sets that are coming, you will find someone who will do the 1 by kth fraction. But now the way the sets are, it could be that you were maintaining some set in the beginning, right? But some element you try to add it to it, it did not give you 1 by kth of this, so you let it go. You added some more elements, now none of them gives, but elements which you have forgotten could be added, and that gives you a good marginal value. So definitely we have a very simple k-pass algorithm which will achieve 1 minus 1 by e factor, like just go run through k times, that's very clear. But if I have to fold it up into one algorithm, we just don't know how to do this, right? And the reason being, if the element has gone by, maybe it was not adding its marginal utility that much, but after a set has been enlarged, it might be adding the marginal utility a lot more, okay, or maybe not. But if it is not maybe not, then we have to prove it, right? It is not obvious anymore. Okay, so let's, okay, f value, we get 1 minus 1 by e, which is 0.6 something something factor approximation. What does it imply? It implies that we have, for max cut, we get better approximation algorithm, right? Doesn't it imply it? Right? For max cut, normal max cut, we get better approximation, right? You just now said that max cut, because cut is a submodular function, I want to find maximum cut, right? All you need is half. all we knew is half, hence the 0.623 approximation, right? Like people know much better approximation algorithm, that's a different thing, but here's a non-trivial approximation algorithm. Okay, so first, so I told you the difficulty which we are going to face if we are going to generalize this algorithm to streaming setting. So first let's see why this approximation algorithm does not work for this and try to rectify this for the streaming setting, and then we will come back in the next lecture and try to first do static setting for the for arbitrary function and then do other things. So we did the same argument twice now. Okay. And the point is, for you example, I would say, so after I've done the basics, like taught you the basic set of algorithms for these things, it will be nice to go and check what is the current status of these problems are, right? What is known, what is not known, people are, how much people have been able to push, how many space, how many, like, right? So for example, if I allow just one pass, can I achieve the what is best in static setting? I mean, things like that. Okay. I mean, this is how you build up your literature on the topic, right? You know the basic algorithm, right? This is what one has to remember. Rest is creativity. Okay. Right? So let's consider the following example. N is like, my N is universe, A1, A2, and I will define a non-negative function because this only works for the non-negative function. So why should I expect? So define a non-negative submodular function as follows. Okay. So what is this? Is 1 if S is exactly equal to A1. Okay? Or if cardinality of S is 1 and S equal to A1. Okay? Half if mod S is equal to 1 and S is not equal to A1. Like, so what we have done, An assigned half to this, sorry, assigned 1 to this, assign all of these guys half. Okay? Okay. Here you need bit of trickery. Okay? 0 if mod S is greater than or equal to 1 and A is inside S. So any set which contains A and which has a larger size, greater than, strictly greater than 1, I have put 0. And otherwise, what will we do? We just sum those elements. Ai in S, f of Ai. Okay. Why this function is submodular? First of all, this is submodular function. So first of all, we have to show that this is a submodular function. So let's use this definition, right? Is this submodular? I take A, B subset of n. So first case, A1 is in A, say A1 is in A, what happens then? If both A and B are a single quantity, then it's fine, right? I mean, so now I pick up any other element. Suppose A1 is in A. Suppose A1 is in A. So clearly A1 is also in B, right, by definition. Now you pick some E element, some AJ element of n minus B. What is its utility when you add to A? It doesn't matter. Its utility is 0 both ways. So that's fine, right? Okay. Second case, A1 is not element of A. But that doesn't mean that A1 cannot be in B. And A1 is in B. Okay. Now look at AJ. A1 is not in A, right? So if I add AJ to that set, AJ to that, I mean it will give me some non-negative number, but here is going to give me 0 because A1 is inside this. You added AJ, mod S is at least 1, so its value is 0. Okay, fine. Third case, A1 is not in A, A1 is not in B. Alright? So when you added a new element, it is just going to add half here and half here if it is AJ. Right? And if you are going to add A1, then it is going to give it to you 0. So this is sum modular. See, this is much easier way to show even for cuts and all. So I find this. So we should be using this definition from now onwards. Okay. So this is sum modular. S is empty. Select an I that maximizes f S union I. Okay. What is S going to have after first iteration? A1. Because now can he add any other element? Can he add any other element? Well, it can add, but that will decrease the utility, right? That maximizes f of S union. It makes it less, so it is not. I that maximizes, so this is it. It will stop at S equal to A1. Right? But if I would have taken S equal to A2 to AN, this is like n minus 1 value, this is 1. So greedy is too bad. I mean, it's nowhere near even constant factor approximation. Okay, good. So that's all that I wanted to show to you people. Okay, that alpha here, f of S, f of f is like 2 times n minus 1. So it's just very bad approximation of it. Okay, so just remember that this particular greedy fails. Okay, okay, good. But maybe a natural idea would have been that, oh, you failed because you chose the wrong thing. So maybe I should start with whole of n and keep deleting element whose deletion increases the utility. Look, if I delete an element, right? For example, if that would have been the case, what would I have done? I would have deleted A1, right? So I could have another greedy algorithm where I start with n, delete an element, but we can show that is also as bad as this. But a combination is good. Okay, but we'll not get there, for at least not today. We'll get there. Okay, okay. So now we would like to do this in streaming. Do I have my lecture notes? कुछ तो किया हुआ है. Okay, streaming. Okay, for that we know this was, right? And again, streaming monotone, right? Monotone. I don't think we need non-negative. We may not be able to achieve this approximation, but we'll get somewhere. And I also told you the Z. So what is the Z? Let Z be the opt value. Okay. This way. So I was telling you, right, like maybe some element went back and in the beginning itself an element who could have added some good contribution came and went away. So we couldn't add it. So let's try to see that if I change this greedy algorithm a little bit and let's say maybe 1 by k is not easy to prove, maybe some other fraction is easy to prove, and that could give us a good algorithm, and we'll try to set up that alpha accordingly. One second. My throat is like saying don't teach, but I have to teach. We'll do this and then we'll stop. Okay, so and we know how to do this. Okay, so for example, okay, so let me write down the full algorithm because maybe I'm using this term very. Okay, so what is the problem? Find S that maximizes f of S more or less equal to k. Okay, so here's my algorithm. Okay. It makes guesses Z equal to, so this we will do in parallel. Okay, 1, 1 plus epsilon square, 1 plus epsilon something, okay, dot dot for opt. Okay, so it will only going to work when we know that opt is not too large. Okay, for opt equal to max a mod a less than equal to k f of a. So we are going to guess these numbers. Okay, and this, since it will be logarithmic in number like some poly n value, for most cases we are interested in. So this will be just like some, and you are just doing this parallel. So I say, okay, I am going to store a set with respect to believing that my value is z is 1, other is 1 plus epsilon, other is, and whichever is the best value I can come up with, I can return this. So this is what I mean when I say do this in parallel. Okay. For guess z, what are we going to do? Okay. S equal to 5, S is 5, and add an element. Okay, so they are coming in stream, right? U in U to S if how have I been writing? Oh, gross. Some people write it as like FAU, some people write FUA. Anyway, it's all over the place. Doesn't matter. Let's follow our notation. If FU union A, what we wanted? If you got Z over K, then they are great. But we don't know how to do this for now. Okay, so let's just write it down some beta K. Okay, we'll see what beta is. Beta is some natural number for now, right? So beta is 1, then it's like great for us. Okay, we'll fix this beta, and that will guarantee the approximation factor. And what else should I assume? And if mod A is less than, then only I should be doing this. Okay, we'll see what is the approximation factor of this algorithm, right? So algorithm is very simple, right? Look, I'm just still trying to do exactly the same, but I really do not know whether this is going to succeed or not going to succeed, right? And if it is going to succeed, why it is going to succeed? Right? So there are like, think of this, that what these Z are is like log n tracks. There are different tracks for Z, right? For each Z I'm maintaining, I'm going to get some other set. So let's call it S1, S2, right? So this is like Z equal to 1, I get 1S. Z equal to 1 plus epsilon, I get another S. Z equal to 1 plus epsilon square, I get another S. Z equal to 1 plus epsilon times dot 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 something star, I get another S, and from them I output the one which maximizes. And everyone is maintaining the constraint that their sets has size k. So I output the ones S, right? Output S which maximizes f of s. Okay. So I have several candidates because I really don't know what the value of z is, and I need that value of z to do this. Right? Because in some modular function I do not know z. If I were doing a coverage function, then I knew, oh, n over something, right? So z was given to me, right, is n at most. So there is some lower bound on this. Actually there also we don't know. Even for maximum coverage we don't know. For set cover we know, but for maximum coverage we don't know. But that's okay. So assume that some O is the opt set. So Z is like f of O, right? There will be something which is between this, right? So look at the first Z for which Z is greater than equal to f of A, then Z is between this range, right? Agreed? So, no? So let Z be in this range because I am guessing all Z, right? So maybe I check is the real Z where it is. So it will be just 1 plus epsilon factor away from f of O, right? Okay. And okay, so first let's assume that mod A is equal to K, exactly equal to K. Okay, sorry, K and S equal to E1, U2, UK. These are my S. Then let's write it down. We know how to now. F of S, right? Let us write it down with respect to marginal utility. How do we write? Set smaller, 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 bigger, bigger, right? So this I can write it down I equal to 1 to K, and imagine that this is the way things had been added. U1 was added first, U2 was added first. Doesn't matter, but suppose now. Then I can say I equal to 1 to K f of Ui to U1 minus f of U minus 1 U1. Right? So what is this? Again, I have done nothing, and this is the third time I am trying to do this, and this is a trick which you have to do always if you want to use the marginal definition. Like this is a very common trick in some modularity if you have to apply marginal. Otherwise, how will I say something? Right? So what is this? I equal to 1, what is this? This is f of U1 minus f of phi. I equal to 1, so this is f of U1, and rest what is? The second will be like U1, U2 minus f of U1, right? F of U1, U2 dot 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 UK minus f of U1, UK minus 1. I mean, I shouldn't be writing this, doesn't matter. This is like U2, U1 because the way I am writing, UK, K minus 1, U1, K minus 1, U1, right? Rest everything will get cancelled. What will not get cancelled is this term and this term. So this happens with equality. Great. Okay. And what do we know about this? What do we know about this? At that point of time, Ui, when you were adding to this set, this was it, like Ui were adding to the set, it was adding at least this much of utility. Look, it was adding at least this much of utility every time. So each of this term is at least z over beta k. So it is k times z over beta k. So z beta. So if you could set beta equal to 1, then we are solved. In this case, at least we are done. Okay. So if this happens, we are very happy. Strictly less than k, and this is a fun part, right? Here, doesn't it look like I should just set beta equal to 1. Right? So f of s which you have given is at least equal to z. So this is fine. Okay, this is like it will take you more 5 minutes. This is one page of computation. This is not something very. Okay, so now we are in the case mod s is less than equal to k, and now let's write it down. O minus s. So here is my optimum solution, and here is my S. And what is O minus S? Is this. Is equal to, I am writing on purpose, A1, A2, AL, and what is O intersection S? Optimum could have just taken K, guys, right? Optimum could always get K, guys, remember, because it's monotone, non-negative, all the things, right? So I just added something, so I can just assume. But this algorithm may not be able to do, because the point is, I mean, I am only adding this when this guy increases my utility, like marginal utility to add it is this much. And look, and this is why you have to write it always like this, because it's like, oh, this contribution minus this contribution is at least this much. So you are basically trying to write the whole sum into small sub sums the way you have added them. There's nothing more fancy happening here, right? So it's just that you have a f holding on to you, but your algorithm is guaranteeing that this f which you are holding on to, when you add a new element, it increases the value of f of s by at least this much. That's all that it is. Okay. And let's define aj equal to okay, find aj equal to this set. Okay, and this is my set the way we have constructed. Let's look at Sj, which is u1, u2, dot 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 qz. Okay. No, Sj is not this. Okay, let's not write it this. Okay, Sj be the subset of S when Aj arrives. Okay, so Sj be the subset of S when Aj arrives. So look, these elements are coming and I'm maintaining Sj like some set. So look at the step when Aj has arrived. Let's call that set Sj. Now you tell me, why did you not add Aj to this? There was some reason. You look, Aj is from A1 to Aj, like, so these element A1 to AL is like in O minus S. So when this guy arrived, you did not add Sj because it was not adding this much value to your this. Agreed? So what can I say in value language? I can say f of Aj agreed? Okay. But S is a superset of Sj. By submodularity. This happens. This is by submodularity. Like S contains Sj. Okay, so this happens. Like nothing fancy has been applied. Okay, and we are done now. So once this inequality is done, right, you are done. So let's consider f S union O. What is minus f of S? Okay, so I want to write this quantity again as a marginal sum. Look, it is nothing a big math, but if you don't do computation all by yourself, you are going to mess around. J equal to 1 to L. Right? Why? It's again just what is J equal to 1, right? So this is F S union A1 minus F S union AJ minus 1, which is A0 is empty. So this is phi. Okay. Plus F of S union A2 minus S union A1 dot 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 F S union, what is that? A L, right? L, which is equal to A1 to AL, right? Minus F of S intersection A L minus 1. Everybody will get cancelled except this term and this term, which is this. And what is S union AL? S union AL, nothing. I'm just following the last protocol, nothing else I got. It's just that now we have to be careful. Okay. So this holds with equality. What is this? What is this? This is a marginal for with respect to what? AJ. Agreed? This is exactly equality, right? Because what will you get if you add AJ little to this? So this minus this is a marginal. And what is this? It's a marginal with S union AJ minus 1. So this is a marginal with respect to Sj. I told you what Sj is. Why? Because Sj is contained inside S. Okay. J equal to 1 to L. Now I expand this marginal. What is this? Sj union Aj minus F of Sj. But what is this? Marginal. This is nothing but I could have written F of Aj Sj is like Z by beta k. Right? So this is like L times Z by beta k, but k is greater than or equal to L. So this is like Z by beta k. But what is Z? 1 minus epsilon times F of A. O. Because L and K will cancel out each other. L is less than or equal to K. So this is less than 1. L is less than or equal to K. So this is less than 1. So 1 minus epsilon times, what did we get? f of o, right, by beta. No, 1 plus epsilon times f of beta. Because we assumed, right, where was f of a? F of z was between 1 plus epsilon times f of a, at least f of o. Okay. So now let's write it down. What is f of s? F of s, because this is what we want, right, is greater than or equal to, I take this two inequality, f of s union o minus 1 plus epsilon times f of o by beta. Agreed? Now this quantity is at least f of o by monotonicity minus 1 plus epsilon times f of o by beta. Do you agree? So this is equal to, if I really have to do maths, so beta times f of o 1 plus epsilon times f of o divided by beta. So if I take beta f of o common, right? If I take f of o common, so then what do I get? I get beta minus 1 plus epsilon divided by beta, Agreed? So what should be the beta? Look, this quantity has to be at least 1, no? F of s, if this is less than 1, I mean this cannot happen. Look, f of s cannot be less than f of o, right? Because o optimizes, right? So this quantity has to be less than or equal to 1, no? Okay. Do you get my point? Huh? Why? Substitute beta equal to 1, does it hold? If I substitute beta equal to 1, 1 minus 1 is 0 minus epsilon so beta equal to 1 definitely doesn't hold. But what about beta equal to 1.1? Even if epsilon was 0, forget about epsilon. We need beta minus 1 by beta should be greater than or equal to 1. Otherwise, sorry, less than or equal to 1. Should be less than or equal to 1 or greater than or equal to 1. So if this is what it is, no, this seems like something weird, no? Doesn't it seems like something weird? I would like to minimize beta. Okay. So what do we get here? So what is an approximation factor? So approximation is like f of a o is less than or equal to right, beta times beta minus 1 minus epsilon times f of s, right. This is what it is. F of O is less than equal to this minus this f of s, right. Yeah. So this should be less than equal to 1, because if it is greater than equal to 1, so what I am saying, yeah, this should be strictly less than 1. Look, I cannot say this is less than equal to f of s, right. Can I say then how will should look, this should be less than equal to f of s. So what should be this? Have we done some correctly? I think I think we didn't do something correctly here. Is this correct? Beta times f of O minus 1 plus epsilon times f of O. So I took f of O common, so beta minus 1 minus epsilon. This is fine. What happens if we substitute beta equal to 1? Let's substitute beta equal to 1.5 and let's see what goes wrong. Okay. So if I suppose we don't have epsilon, like we knew z exactly. Okay. So if I do 1.5 and beta minus 1 is 1.5, so this is like 0.5, so this is like 3. Okay. So basically not, this is not the question is. The question is minimize beta by beta minus 1. This is what I would like to do. I want to minimize this ratio, right. So when it will be minimized? Look, if I want to get a best approximation, I should minimize this, right. Forget about epsilon for now. So when will this? Huh? So my f of x is x by x minus 1. When is this minimized? Huh? I understand that, but what is their value? This is exactly what I want. Can I take x equal to 1.9, let's say beta equal to 1.9, then what is beta minus 1? It is 0.9. So this is also more than 2. Good. So I cannot take beta equal to 0.9 for sure. If I take beta equal to 2, this is fine, right? Is 2. So if I take beta equal to 2, this is perfectly fine. But what happens if I take beta equal to 3? Which is? Huh? Better, right? So why can't I take beta equal to anything? Huh? I understand. I take 1000. I will take. But this shouldn't be correct, no? Huh? What? Where? Yes. What size? There's no size. This is like marginal. Yes.
So if you keep on increasing beta, then you're picking almost every set, more and more sets.
I'm only picking k sets. Okay, so this is clear that beta is at least 2, right? Look, I mean, we shouldn't be breaking or maximize beta minus 1 by beta, whatever, because if you are talking in terms of, okay, or maximize beta minus 1 by beta. The reason why I wrote it this way, because now if I fix beta equal to 10, what happens? Maybe 9 over 10. We should be getting that close. I mean, 0.6 something is a barrier. So where are we making a mistake? I understand we cannot take k equal to 1, but fine. What, like, there should be something wrong. That, I mean, like, if you're telling that you're picking things with threshold much larger, you should be getting bad ratio. You at least need 2, otherwise, I mean, I shouldn't be able to pick beta equal to, I mean, 2 should be the best for us. Here it is. You also have z by beta, right? Here, this case, when you pick exactly k set, what factor approximation you are returning? Look, here it is z by beta, right? So if you choose beta equal to 10, what are you returning in this case? 1 by 10 approximation. So while in this case you are doing good, you are doing very bad here. So what you would like to do? You want to maximize 1 over beta, comma this. And when will this happens? When this is equal. So now you set 1 by beta equal to beta minus 1 by beta. So what do we get? Beta equal to beta square. Is it correct? No? From here, this is what we will get? Yeah, 2 beta equal to beta square. So beta get cancelled, beta equal to 2. So set beta equal to 2, right? This is where the problem. We had 2 cases. Of course, we were optimizing great in one place. There was nothing wrong in it. It's just that you were making some other place worse, right? So you substitute 2, fine. Then what approximation of them did we get, right? So look, but it says still something amazing. What it tells you? That, well, we may not be able to get an element whose marginal is like 1 over k, but we are able to get an element with marginal 1 over 2k. Right? You understand my point? We are not able to get an element with marginal 1 over k, but we are able to get an element with marginal 1 over 2k in streaming. Right? So this gives us, if you do all this, it will give you, okay, so this has ratio, how much? If you notice, it is like half minus epsilon, right? Because this is like 2 minus epsilon is like 2 minus 1 is 1 minus epsilon by 2, so epsilon by 2, so you just choose epsilon prime slightly larger. So you run this algorithm. So this is what you will get. Okay. So next time we will talk about non-monotone, like arbitrary monotone functions.